average rate of change. So if we wanted to look at the average rate of change of a function, we could consider this example. Suppose we wanted to find the average rate of change for the function f of x equals x cubed minus x over the interval 1 to 3. So if you graph this thing in your function, or in your calculator, this is what it would look like, or something like this. Kind of goes up through -1, has a 0 there, goes up, we don't really care, and then it goes through 0, and then back up through 1, and in fact it's kind of got even more of a slight curve like that. Alright, so this is at 1. It looks kind of like that. And we want the interval from 1 to 3. So since I drew such a nice graph here, we'll call this 3. And I want the average rate of change. Well, it turns out the average rate of change over that interval is the slope of the secant line on the interval. So we'll kind of, let's put a little definition over here so we can refer back to it. The slope of the secant line is equal to the change in y, remember that's the change of the function, divided by the change in x, or the time it takes to make that change. And we could define that as, in function notation, we could say, well, hey, you're just really taking f of b minus f of a divided by b minus a. Well, it looks a lot like the slope formula. Okay? And in our little example over here, this would be a, and this would be b. 1 would be a, and 3 would be b. Questions so far? I rocked your world yet? Well, this is like a Monday, even though it's a Tuesday, isn't it? It's got a Monday feeling here. Yeah, all right. It's worse.
No,
okay.
Instead of Thursday, it's actually Friday.
All right, so what we're looking at here then is the slope of the secant line, and the secant line is, I'm going to draw it in a different color and dot it for your learning convenience, but this is the secant line, and what we're looking at is the slope of this thing from 1 to 3. We want the slope, so we're going to take this point here, which I'm just going to label in general terms as 1 comma f of 1. And then this point up here I'm going to label as 3 comma, what do you think? F of 3. That's what I like about you guys, nothing gets by you. 3 comma f of 3. Alright, and so if I want to find the slope of the secant line, or the average rate of change of the function over that interval, I'm just going to plug it into my little formula here. So the slope is going to be f of 3 minus f of 1 divided by 3 minus 1. And so I end up with a slope of 24 minus 0 on top, divided by 2, and that's just a slope of 12, they said. 12. Okay, so the average rate of change of that function over the interval from 1 to 3 is just 12. Okay. Questions on the average rates of change? Good, okay. Now, remember we said the average rate of change is a kind of an estimate, and if we shorten the interval, it gets to be a better estimate. Let's look at what that let's visualize that graphically. So let me turn on my projector here, and see if we can visualize what we mean by kind of taking this, the interval, and shrinking it down to, well, it's nothing actually. Leave that up there. When you guys hit the lights? Thanks. Well, okay, now I need one. No, wait, maybe I don't. Maybe I'm okay. No, I'm okay. You can kill it. I already forgot what colors we said were good colors. Black, blue, and
It was
green.
black, purple, and
Alright, so suppose we had a function, and I really don't care what function it is, but suppose it's a curvy function, and it kind of looks like, oh, I didn't even put grids on this. Perfect, I can draw wherever I want. And it looks kind of like this. Can you guys see that function okay?
Yeah.
Okay. And suppose that we wanted to know what the average rate of change was right here. We'll call this point A. Any A, but suppose if we wanted at a point, x equals A. We wanted to know what the average rate of change. It's very similar to that question we asked. What does it mean to be going 58 miles per hour at 2:03 p.m.? This is 2:03 p.m. I want to know exactly what my rate of change is there at A. Okay? Well, what we did before is we said, well, you know what you can do is you can take an average. And we just said, well, that average is the secant line. Hope green's alright. You guys see green okay? Okay, so we said that was the secant line, and we'll represent it with the dotted line. And we said that the slope of that thing gives you the average rate of change over the interval. And everyone said, oh, well, that's okay. So, you know, here's my interval to that point, and I don't want to give this point a name. Let's just call this distance h. So let's call this distance right here h. Okay? So what we're going to do is we're going to take h and we're going to make it smaller, going to the bringing h closer to a. Okay? And then you guys said last week, you told me, well, if you make the interval smaller, you get a better estimate. So let's check. I'm not sure if I believe you, but let's take this point right here maybe, and let's draw in a secant line. I'll try and be careful here. And it looks like we're getting closer. What are we getting closer to? What do you think we'll end up at here at A? If I keep shrinking the secant line down, so here's my next point. We're taking A plus 8. We call this point A plus 8. And we're shrinking h down. If I keep getting closer, what does the secant line start to become?
A line that almost equals the original function.
Yeah, a line that equals the instantaneous rate of change. What's the name for a line that only goes through one point? Like you learned about it in circles, I think. Tangent. Yeah, we're getting very close to a tangent line. Wow, I think that's going to be a big deal. Let's try a different color here. Did we say blue? You can see blue?
Yes.
Okay, all right. I'm going to draw in the tangent line here in blue. So the tangent line is here in blue. And the slope of this thing is the instantaneous rate of change at A. The slope of the tangent, that might be worth writing down. The slope of the tan line is the instantaneous rate of change at point A. Take a second, write that down, absorb it, let it melt into your brain, and let me know if you have any questions. Okay, now this is all great, but it doesn't tell me how to find it. Now, a few of you last week alluded to this idea that, you know, what you're really doing is you're letting, we could use limits to shrink this value down infinitely close to 0. In fact, what would we say we're letting get close to 0? What value is getting close to 0? This distance right here, what do we call that? H. We're letting h go to 0, so I might even write that in there somewhere also. H is going to go to 0. So I'll kind of preface the next graph with that. We're going to let that h go to 0. Can I erase this and draw the next one? Okay. All right. So the next graph is the definition, the proof of a derivative at a point. The proof of the derivative at a point. The slope of the tangent line at a point.